Okay, so here's where we were last time. We were talking about change of variables, right? A quick reminder, remember the big idea with change of variables is to realize that it's morally equivalent to substitutions. If you take the point of view on substitutions, which we never do in single variable, but if you take the point of view on substitutions, that what you're doing is you're doing a pullback, right, through a function. What you call the substitution function is really a change of variables function through which you're doing a pullback, and that the extra factor of g prime is just it's how much do little pieces of the pre-domain, the pullback domain, get stretched out into the output domain, right? So pullback, stretching factor point of view on substitutions. Change of variables is just a two-dimensional version of that. Okay. All right. So we started this example last time. The idea was that we had these four curves, which look kind of like this. We talked through approximately why that is. We're interested in the region which is bounded in between those four curves. So we're interested in that region. Right? Yikes. Think about how you'd slice that up if you did that sort of the old-fashioned way. I mean, there's going to be three different pieces, and again, so highly undesirable. Notice that if you set up a change of variables function, what I'm going to call anyway a change of variables function, but if you have it going backwards, these curves, like for example this one, with that equation, xy equals 6, well, if you set u equal to xy, that becomes just the curve u equals 6. It becomes a straight line. And thereby, our highly undesirable domain there turns into, instead, well, just a rectangle. Everybody's favorite domain for a double interval, right? Constant bounds, one chunk, no problem. Okay. All right. So that's nice and all, except we do have to recognize, well, the function's going the wrong way, and can you do that, and is that a thing? Well, remember we argued just before this example that, if the function's going the other way, all that means is that with the stretching factor that you're going to compute, just take its reciprocal, and that will give you the stretching factor for the function going the right way. So conveniently, as another example, and I went on a little aside about this, this is another motivation for using a notation that looks like a fraction in writing down the formula for the stretching factor. Now, it isn't a fraction, it's a determinant, right? But it behaves like a fraction in this sense, and so we're going to write it like a fraction for convenience. Okay. So looking at the change of variables function going this way, I can compute the stretching factor. The partial of the output variables, here's your output variables, u and v. Their partials with respect to our input variables, x's and y's. Right? That stretching factor for that function, the partials of the outputs with respect to the inputs, easily computed. Bam, there it is. Notice, of course, this is not the stretching factor I want. I want the stretching factor for the function going the other way. So I take the reciprocal. Okay, so really nice trick. And with that done, it's all sort of downhill from there. So let's see. So notice what I need. The stretching factor I need is partial xy over partial uv. And here it is. Let me write this down. That is partial xy over partial uv. And notice, again, in the sort of the good fortune of this, fraction-like notation, it's as if that denominator kind of sort of, it's as if it cancels with that otherwise numerator thing there. Now, of course, that's completely bogus. These are not individual things. There is no actual cancellation. But again, if you think in these outrageously inaccurate terms, it will always give you the right direction and the right answer. So it's a nice little crime to commit. It's a crime that I kind of encourage. Okay. All right. Now there is one little sticky wicket that we have to worry about here, and it's nice to say, the stretching factor is just the reciprocal. Set up the change of variables function whichever way you want to go. It's fine. Let the notation keep track of whether you should take a reciprocal or not. That's lovely. But notice our goal was to rewrite everything in terms of u's and v's, and we did not get that here. Right? This stretching factor was written in terms of x's and y's. Of course it was, because it comes from a function that was in terms of x's and y's. And so my resulting integrand is still in terms of x's and y's, and I need to figure out how to write that in terms of u's and v's. So that's the bad news. On these kinds of examples, when you do this clever move of just have the change of variables function go the wrong way and, sort of do the algebra backwards, you're going to have to figure out the algebra that's necessary to turn a function of x's and y's into some expression in terms of u's and v's. Now, we get lucky in this case. What we're staring at here, this xy, how do I rewrite xy in terms of u and v? Oh, lucky break. Bam, it was right there staring at us. And every so often the fish just jump in the boat. Right? So what if you didn't get that lucky, though? Well, then you have an algebra problem. And you've got to figure out what you can do. Now, I'm going to propose, in this case, if we hadn't gotten lucky, I've got some expression involving x's and y's. Maybe it's x to the m, y to the n, and it's not, exactly something I already have. How would I write, now this is a rhetorical question, if I have a product of powers of x's and y's, and I need to rewrite that in terms of one product of powers of x's and y's, and another product of powers of x's and y's, right? So I have the blue expression on the left, such as perhaps I might have, ended up with there. I need to write it in terms of u and v. These have the same structure. I'm trying to rewrite a product of powers of x's and y in terms of other products of powers of x's and y's. And what relationship do we expect there to be between products of powers of x's and y's and other products of powers of x's and y's? I don't know. Seems like a reasonable guess. Maybe this one is a product of powers of those products of powers. Seems plausible? I don't know. It's a stab in the dark, but it seems plausible. I'm not guessing. I think it would be silly to think that blue thing is like maybe sine and cosine of the green thing and the yellow thing. It seems unlikely, right? So the form that you're dealing with will sometimes suggest a possible answer, a possible relationship. How can I write x's and y's, products of powers of x's and y's here? How can I rewrite that in terms of u's and v's? This is suggested by the forms. It's just a suggestion. Every question is going to be different. You won't always have some product of powers of x's and y's. It might be totally different. The functions that you're trying to rewrite in terms of might not be this. They might be something totally different. So, but anyway, you might have to make a guess as to what the relationship is, and then solve for your fudge factors, right? So I don't know what these a's and b's are, but if you write this down and go through, you can then subsequently solve for and see what your a's and b's are. You can solve this, right, for a and b. Okay. All right. Okay, what about 3 dimensions? Good news. It's like exactly the same thing. It's really very, very similar. If you want to do change of variables in 3 dimensions, and by the way, you really, really might. For example, suppose that you have a domain that looks like this. Right, something like that, some big warped, bent around solid. Whew, you just can't even imagine how many different slices there are there, right? Think about how you'd slice that up. How many corners are you going to cut through? How many side swipes are you going to have on faces? How many side swipes are you going to have on edges? I can't even, right? So, wouldn't it be nice if I could view that as being the image of a nicer domain? Wouldn't it be lovely if that was the image of, let's dream big. Wouldn't it be nice if it's the image of a box? Everybody's favorite three-dimensional domain. If it is, do a pullback. Right? Take your expression that's defined on this ugly domain, just rewrite everything in terms of U's and V's. The nature of the pullback is just like the nature of the pullback we did for two-dimensional change of variables. It's just like the nature of the pullback that we did for one-dimensional change of variables, namely the substitution rule. Namely, points over here in the XYZ world, we already know that they are G of points over here in UVW world. Right? We already know XYZ is G of UVW. So plug that in. There you go. We've gotten rid of some of our X's, Y's, and Z's and turned them into U's, V's, and W's. The plugging in will always be just plug in. Right? The big question, of course, is what to do with the volume, right? How much volume there is in the image little chunk over here is not going to be the same as the amount of volume that there is in the pre-image chunk, right? This little piece might get stretched out by the G function to become that little piece. How much does it get stretched out? Good news, the stretching factor takes a very similar form. Again, I'm not going to prove that right here. We'll motivate where this formula comes from later. We could do it now. We have the tools. There's enough going on with the mechanics of how to do change of variables, and we need to get to other things. But we're going to come back at an appropriate time and think about where this comes from. But anyway, the point is, the formula is the same. It's the absolute value of the determinant of the Jacobian matrix. It's just that now it's a 3x3 Jacobian matrix because we have, of course, 3 output variables whose partials we'll be taking with respect to 3 different input variables. And I see now that I forgot to write U right there. Sorry, typo. There's a couple other typos we're going to see today in my notes. Sorry about that. So 3x3 matrix to take the determinant of instead of 2x2, but still same form. Okay, so the example here is in the notes, is very, very similar to the mechanics that we saw with two-dimensional change of variables. So I'm going to let y'all read this example on your own. It's a pretty straight read, and I'm going to move on to the next thing, which is symmetry. So now recall, we've talked about symmetry theorems. Y'all know I'm a big fan of symmetry theorems. Right? The justification I gave you at the time was Riemann sums. You look at pieces on this side, you look at pieces on that side. If it really is a reflection, if the function really has odd symmetry, you can just look at individual terms in the Riemann sum. Those little terms in the Riemann sum clearly cancel. So that's a nice point of view. But I want to point out that change of variables gives you another way to justify, another way to think about why symmetry works as a theorem. And so the idea is, if you view a reflection as a change of variables function, that's the big idea. I appeal to your geometric intuition. If you do a reflection, areas don't change, right? I mean, it's a reflection. It's not a funhouse mirror reflection, right? It's a reflection over a line or in 3 dimensions through a plane, and volumes stay the same, areas stay the same. So the stretching factor is 1. So let's consider then this case of, suppose I have a change of variables, a reflection as a change of variables function. Suppose my domain is symmetric. Suppose my function has odd symmetry. And let's think about an integral. We're looking at a 2-dimensional case here, and let's just start messing with it and see what happens. Well, first thing I want to do is observe that because the domain is symmetric, the domain is its own reflection. It's kind of what symmetry is, right? Nothing deep there. Now check it out. I'm doing an integral over an image domain, and so I can apply change of variables. I'm going to do a pullback. This is a pullback through this change of variables function. Straight up pullback, right? The integral over the image pulls back to an integral over the, what I like to call the pre-image, the pullback domain. Stretching factor is 1. And then, don't forget the function has odd symmetry. Because the function has odd symmetry, the value of f at the reflection is the negative of the value of the original value of f. And lo and behold, we're actually kind of done. Believe it or not. I mean, that little quick argument, and notice the punchline is that this integral, this integral is the negative of itself. How could that be? What value could this integral be that is its own negative? Well, of course, that means that this integral is 0, and there's the result. So nice, quick, easy. I'm going to call it a proof. I skipped a detail, but it doesn't involve Riemann sums. So some people like this a lot. If you want to change this to an argument about triple integrals instead of double integrals, all we have to change is we have to make the symmetry over a plane. We turn these into triple integrals instead of double integrals. dv instead of dA, and that's the proof. It's the exact same argument in 3 dimensions. So that's something to think through. Okay. All right. Okay, so we're going to move on to a new topic today. We're going to talk about coordinate systems, different kinds of coordinate systems. There's a reason that we're doing this now that we won't get to today, but we will see on Friday. We'll see a really good reason why this is the perfect time to introduce different coordinate systems like polar coordinates and cylindrical coordinates and spherical coordinates. Let me call your attention, by the way, to this relates to another thing. In Chapter 14, I'm bouncing around in the syllabus quite a bit. Y'all recall we were doing triple integrals. That's 14.6. And then I don't know if you noticed, but then we jumped right up to 14.9, change of variables. We kind of skipped a couple other sections. And now we're jumping back to, momentarily we're doing Chapter 10 and back to Chapter 12, doing spherical coordinates. And then we're going to jump back up and do section 14.4 that you may also have noticed we temporarily skipped. All this bouncing around is because in order to take a certain point of view that I think is wonderful, I have to do the topics in a slightly different order. And it doesn't make any difference. It's something I've been doing for many years, but anyway. Okay, so heads up on, notice that as you're doing the homework exercises, don't just do the next one, right? Look at the lecture schedule, see which ones are actually assigned based on what we've actually completed. Okay. All right, so polar coordinates. Everybody's aware of the idea of XY coordinates for a point in the plane. You give me any point in the plane, and there's corresponding XY coordinates. And by the way, vice versa. If you give me XY coordinates, there's exactly one corresponding point in the plane. So this is what I like to say, rectangular coordinates are unique. Right? There's a perfect pairing between points and coordinates. Okay. So that's not true of polar coordinates. Right, here's the idea of polar coordinates. If I were to describe to you the location of a point in R2 by way of, what is this angle? And by way of, how far in the direction defined by that angle, how far do I go in that direction? Okay, that's a way of describing where the point is, but polar coordinates are not unique. And it's not too hard to see. So for example, I could think of this as being, as coming from, this angle and that far in that direction. But I could also think of it as that angle, right? I could have that angle theta. And in this is going to seem weird, but in that direction, right, we've got this direction in which I'm going to go backwards. And I'll just correspond to the r coordinate being negative. Oh, come on. It's just a negative r. Okay. So they're not unique, and also, for your consideration, this angle, I could just go around another full turn, 2 pi. Same eventual direction. I would get the same point in the xy plane just by way of different polar coordinates. So that's one little heads up, a little warning about polar coordinates. They're not unique, and this causes little annoying problems here and there. Okay. The point of view that I want to give you that I think you probably have not seen before on polar coordinates is that I want to think of them as a function. This is going to be a big deal for us. Don't think of polar coordinates as just like a different way of thinking about locations. Think of it as a function. If you give me an r and a theta, r and theta go into this function, right, and out comes the x and y, which we already know is uniquely associated to a point in the xy plane. Okay, so take this point of view as a function. All right. So we've already talked about the non-uniqueness. So again, thinking about polar coordinates as a function, notice that adding 2 pi to the angle. See, I'm adding 2 pi to the angle. This takes you around a loop, gets you back to the exact same point. Right. Along those same lines, again, thinking of this as a function, if you were to increase theta by pi, and having done that, take the negative of the value of r, that again gets you back to the same point. So a different sort of way to visualize what we talked about before. Okay, so lots of different, failed uniqueness. All of these are polar coordinates of that same point. Okay. All right. Another thing to be aware of is the way we write down polar coordinates. This is just an awkwardness. I'm sorry. It's frustration, but this is what it is. It's not necessarily clear just because you write down an ordered pair whether you're talking about that point's rectangular coordinates or some of that point's polar coordinates. You write down, for example, 1 comma pi over 6. What does that mean? It's possible that by 1 comma pi over 6 you mean that r is 1, theta is pi over 6. I mean, pi over 6 kind of looks like an angle, right? And so if you would just interpret based on an assumption that that's polar coordinates, you'd think you're talking about this point. But there is a perfectly good point where x is 1 and y is pi over 6. There's not a thing wrong with that as a point in the xy plane. So when you write this down, 1 comma pi over 6, this leaves a question. Do you mean that point or do you mean this point? All right, so just be aware of the problem. I've toyed with different notations, like maybe you put a little subscript, R for rectangular, P for polar. Yeah, that has something kind of convenient about that. But anyway, all I'm going to say in this class, just be aware and make sure that what you've written down isn't ambiguous. If what you've written down is ambiguous, and if that's a problem, then that's on you. Okay. All right. Alrighty. Don't be too quick with converting between rectangular and polar. It's real easy to write down. By the way, I have it back here. I didn't bother to mention. But not hard to see from this triangle, right triangle, right, that x is r cosine theta, right, and y is r sine theta. That's an easy little trig argument. So converting that way is no problem. But going backwards, students are very often what I'll call just too sloppy on this. A lot of students, for example, will take this equation and say, but I want to know r, and so I'm going to write down r equals square root of x squared plus y squared. And this is bad. The problem with that is this equation uses that symbol, the square root symbol, which means positive. that's strict, right? That symbol means positive. You are saying, therefore, that R must be positive, but of course it doesn't actually. All right, so just be really careful about that. I mean, I'm a big fan of writing it. Don't do that. Your 50-50 coin flip that you just got yourself in trouble. Right? Just leave it as this. R squared is x squared plus y squared. That's always true. It's fine. Not a problem. And then in the context, you can figure out, well, wait a minute, is it a positive or is it negative? And let's look at the details. Likewise with the angle. If you take this perfectly fine formula, okay, as long as x is not 0. But if you take this other mostly perfectly fine formula, and if you rewrite this as theta equals arctan of y over x, well, now you're making this strong assertion. This function only takes certain values. The arctan function is always between negative pi over 2 and pi over 2. And theta is under no such constraint. Theta can be, you can go around as many times as you want, right? So this formula here, bad. I mean, this is highly worrisome and problematic. Just stick with this. No problem, as long as x isn't 0. And then in context, figure out what the theta is that you're interested in. Yeah?
Couldn't we just say for the r squared, for instance, could you say r equals plus or minus to take care of that, or not really?
It's you can't. I mean, the weird thing about that is now, are you saying r is two different values? Or okay, you see what I'm saying? So I mean, the implication perhaps is that r is one of these, and I don't know which. But it could be interpreted as saying r could be either of these. And that also might not be true. It may be that R is specifically one of them. And it can't just be either one. So I think it's cleaner. There's less potential for you to be writing things down that are false if you just leave it like this. Yeah. Good question, though. Thank you. Okay, I like this little counterexample. A lot of students roll their eyes and think, oh, come on. Uptight mathematician, weirdo, right? Not that that's not true. But still, consider for your, for example, this point here, -1 comma -1. Now, if you take this point, and if you're too fast and loose, and if you're just like, oh, okay, so r is the square root of x squared plus y squared, and theta is arctan of y over x, what you will find is that gives you these numbers, which tell you that point. And you're wrong. I'm just saying, right? Okay, so you got to have a policy that addresses this clear mistake, right? So now, if you do it my way, right, then what you'll find is that there are two possibilities for r, and I'm not sure. Let's leave that undecided. And there's two possibilities for theta, plus 2 pi, of course, right? But it could be pi over 4, or it could be 5 pi over 4. And then once you have these written down, then look at the numbers and look at the point and figure out which ones actually pair up. And one thing you could do, perfectly reasonable, would be to pair them up like this. That says that we're looking at an angle that goes that way, and in that direction we are going a positive distance. And that does give you the correct point. Or you could say, instead, I'm going to pair them up this other way. I'm going to say my angle is like that. That is the direction of theta, and then in order to get to where I want, notice I have to go a negative r coordinate. So, don't play it too fast and loose. Look at the picture, think about it, pair them up thoughtfully. Whatever that's worth. Okay. All right, I'm going to go real quick through these examples. These are pretty straightforward. I don't think it takes a big sales pitch to persuade you that if I write down r equals 3, that gives me this circle. Okay. Likewise, if I write down theta equals pi over 3, well, I mean, right, that's all the points for which theta could be viewed as pi over 3. So, okay. For other ones, just plug in. Now, there's some more typos in here, and I apologize. I was writing this down too quickly, but this should be square root of 2 over 2. 2. Sorry, I heard myself talking as I was writing. So please make those edits. But anyway, the point is you can just start plugging in some points. This is just plain old plotting. This is just plotting in polar coordinates. Start looking at different angles. For each angle that you look at, figure out the corresponding value of r and go that corresponding distance in those directions that you've decided on, and start, you plot points and you can just kind of almost trace through and see what your curve looks like. And there's some kind of weirdo, wacky examples, and these are interesting, right? So this one here, r equals sine 2 theta, does this weird move. And it goes around like this. Well, that's neat. It's just what it is. It's fun to kind of plot through. It's a nice exercise. I encourage you all to plot through some points and persuade yourselves that it does this. Notice r can be negative, and it is, often. And as a result, it jumps through the origin a bunch of times and makes a little four-leaf clover, which is kind of neat. And then likewise, this other one. Now, this other one's a little bit less pretty, I think. It's subjective, right? But this gives you a shape that has a little bounce in it. It's like somebody took a circle and just kind of poked their finger from the bottom. Okay. All right. Converting equations between one coordinate system and another is not particularly delicate. There's some little minor things I want you all to be aware of. Let's take that circle that we started with, r equals 3. If I wanted to write this in rectangular coordinates, how would I do it? Well, recall, I'm really uncomfortable converting r, right, into polar coordinates, because r could be into rectangular coordinates, because it could be positive, could be negative, and I don't want to say square root, and I don't want to be ambiguous. But what I could do is take this equation, square both sides. That gets me to this. I am very comfortable saying r squared is x squared plus y squared. There's no asterisk on that, right? And then notice I get the equation of a circle. So what that tells me then is every point on my polar curve is a point on that thing that I know rectangularly is a circle. Now, do be careful. This algebra here does not go backwards. Right? You can't undo that step. Right? You can't sort of take the square root of both sides, etc. But what you can convince yourself just geometrically is that, well, it is further true that every point that's on this circle is also on this thing that I also know is the entire circle. Okay. So sometimes you have to think through little details like that. This one I can convert to rectangular coordinates just by taking the tangent of both sides. And then tangent, of course, is y over x. And there you go, you get a rectangular form of the equation, and you got to worry about, does it go both ways? And in this case, again, lucky break, it does. Okay. Here's a weird one. What does that look like? Now, you don't previously recognize r equals cosine theta. That's not obvious what shape that is. But let's multiply both sides by r. At which point I do get a little bit worried. I think, oh gosh, if I want to go the other way in this algebra, I'd have to divide by r. What if r is equal to 0? We're going to have to worry about something might go wrong when r equals 0. We'll worry about that later. But anyway, multiply both sides by r, and then notice that r squared is x squared plus y squared. R cosine theta is x, and everything has worked out just fine and dandy. This, by the way, complete the square, and you get circle. So that's the neat punchline. This is the polar equation of a circle centered at 1/2 on the x-axis and radius 1/2. That's kind of neato. This is going to be important later, by the way. This specific example, that this equation makes that circle, is going to be super useful. And then similar examples, r equals sine theta, work that one out for yourselves, but r equals sine theta, a different kind of circle. Okay, now let's go back to that whole r equals 0 business that I got scared about. So here, can r equal to 0? Yes. But here, can r equal 0? Yep. So no problem. It's something to worry about, right? When you multiply by something that might be 0, but not a problem in this case. Okay. All righty. This is a hard example. I'm just going to show you because I think it's neat how this works out. Here's a rectangular equation. What if I wanted the polar equation? Which, by the way, very often we will want the polar equation for things that we currently have a rectangular equation. How do you do that? Well, let's square it out. If you do both of these squares, expand. Notice that you're going to get an x squared and a y squared that I can convert into r squared. That's nice. Note that the constant terms cancel the 4. That's nice. The cross terms turn into that. X is our cosine theta, y is our sine theta, and but how do you deal with that? I already converted that into r squared, so I know how to convert that to polar. But how would I convert this into polar? And the little tricky move that I think is cool. Go ahead and write down x is our cosine theta, and y is our sine theta, and then, like I say, this is a slick move. Pull out a factor of 4. Why 4? Well, 4 because then this becomes exactly the structure of a angle addition formula. This being a cosine and this being a sine of a single angle, namely pi over 6. So it's a neat move. Right, so you can look at whatever numbers you find yourself with here, you can think about how to play sort of an analogous move and have this turn out into something that you can rewrite with an angle addition formula. It's like I say, it's a tricky move, but I just wanted to show you that kind of thing is, sometimes doable. Okay. All right. Let's go up to 3 dimensions. Cylindrical coordinates, sometimes called polar coordinates in R3. And I think that's a reasonable thing to call it, but I will point out there are more syllables in polar coordinates in R3. Why not just say cylindrical coordinates? It's ultimately easier. Anyway, all it is just like it sounds, it's pretty much just polar coordinates in the XY plane. And then, by the way, we need a third coordinate. Let's call that Z. So the relationship between rectangular and cylindrical is, there's the polar coordinate business in the plane, and then, in both cases, we just need to know how high up above the plane is the point that I'm actually interested in. So it's pretty much polar coordinates in 3 space. So there's not that much then to say really about it. I mean, it's everything that we knew about polar coordinates applies, right? And different examples. That previously was a circle, but now in 3 dimensions, that's a cylinder. Algebraically, though, we get still r equals 1. Now again, in 2 dimensions, that's a circle, now a cylinder. Different examples. Here is a sphere in rectangular coordinates in 3 dimensions, and notice that equation's still true because again, it's pretty much polar coordinates, right? And so we get a cylindrical equation for the sphere. Then looks like this. Remember, Z is one of these cylindrical coordinates. Okay. All right. So I'm not going to spend a lot of time on cylindrical. It's like I say, it's polar coordinates, comma Z. Okay. The next one, though, spherical coordinates. This one's trickier. This one does require a little bit of discussion. Let's see. Oh my gosh, it's already 11. Whew, man. Okay, so spherical coordinates. By the way, also sometimes called polar coordinates in R3. This is a bad idea. Please do not call this polar coordinates in R3. It's not. The polar coordinate R is not one of these spherical coordinates. The thing that plays the distance that's computed, that's part of spherical coordinates, is a totally different distance coordinate. It's just different. So don't try to associate this with polar coordinates, please. It's a mistake. if you're going to insist on thinking about something as polar coordinates in R3, oh my gosh, for sure, 100%, it should be cylindrical coordinates. Okay, so what are spherical coordinates? I'm going to tell you where a point is by 3 numbers, again, not rectangularly. I'm going to tell you, let's think of that as being in a certain plane hinged on the z-axis, like that, right? I'm going to tell you the angle. That's kind of, sort of polar, right? That's just, in a way, it's the same angle, theta. It's the same theta from cylindrical coordinates, for sure. Okay. And then I'm going to tell you another angle. I'm going to tell you the angle off of the positive part of the z-axis. It's called phi, the Greek letter phi. And between the two of those, between that blue angle and that orange angle, notice that defines a direction, and in that direction you can talk about, okay, well, what's the distance coordinate in that direction? And that's what we call rho. It's another Greek letter. By the way, be careful. That's not a P. It's not close enough. Please don't make a P. P is not the same as rho. And so this is a new letter that you'll have to kind of practice making. And you remember how I told you it's a little bit humiliating, but when we get to partial derivatives, you just got to figure out how to make this new little thing, and you get to practice like you're a second grader. Your new letter that you need to learn how to make. So you have to learn how to make the partial symbol. Well, give some time practicing making your new symbol, rho. And again, not the same as P. Don't make a P. Okay, all right, so those are what the spherical coordinates are. I have them listed here. Well, typically they're written in the order of rho, phi, theta. By the way, there's another little typo. This one was more of a brain absence. But I know that y'all are not previously familiar with the entire Greek alphabet, and so this I helpfully noted here is rho, which I spelled out. And then in my mind I was being helpful. Right? I was like, oh, I know they don't know what phi is, and so I in my mind I was like, oh, it's phi, right? Isn't that useful? I'm sorry. So anyway, why don't I go ahead and write that down? It is spelled in a kind of a weird way. It's spelled P-H-I. So phi. Yeah. Okay. Alrighty. Keep that scratched out. Yeah. Sorry?
Laughs in Greek.
Yeah. That's right. So how do we convert? What's the algebraic relationships here? You just have to look at the picture, and a couple of things that you'll notice. The first observation I like to make, I think this is really valuable, is to notice that, whoops, I meant to do this in a highlighter. This is a right triangle, through which it's easy to argue that R is rho sine phi. So just make that observation. It's a little bit of trig. Because of course, that angle is the same as that angle. Right? And with that observed, notice the first two formulas you need to know for spherical coordinates really are just old formulas you already knew. X is R cosine theta, Y is R sine theta. Just don't forget R is rho sine phi. Right? So easy way to remember those first two formulas. And then having noticed that R is here, let's see here. Let me make this triangle a different color, and then I can color code better. So R is rho sine phi, and then you notice without too much trouble that Z is just another side of that same triangle, and so Z is rho cosine phi. So that's easy to remember ultimately. Side note, in my life I have never memorized those formulas. I've used them countless times. Oh my gosh, physics majors do spherical coordinates a ton, just lots and lots of examples. I have never memorized those formulas. Every time I need those, I think through that triangle. I think through that R is equal to rho sine phi. It's just, you think, okay, yeah, right there it is, and then write these down. Right, so if you want to memorize them for efficiency purposes or something, that's fine, but let that be supplemental, let that be in addition to knowing how to derive them, because I like to point out, I've done it before, I'll do it again, anything that you memorize, you are prone to misremembering. I mean, and by the way, I see that happen all the time. All the time on my exams, I see students who, oh gosh, everything is good here except the student wrote down x equals rho cosine phi cosine theta, and y equals rho cosine phi sine theta, and then z equals rho sine phi. They just get it backwards because they memorized and they didn't think through the picture. Okay. So make sure you understand the picture. Okay. Also, pretty clearly true, and I'm going to let y'all think about the details on this, but pretty clearly true is that rho here satisfies this rule, or if you want to convert to cylindrical coordinates, that rule. But easy observation there. Okay. All right. Be aware of the lack of uniqueness. This example is a little bit of a nightmare. But this is mathematical weightlifting. It's a good exercise. It's probably not going to really actually come up an awful lot, but nevertheless, it's a really good exercise in thinking about spherical coordinates. But it is really uncomfortable. So maybe this is mathematical crunches or something. Nobody wants to do it, but it's good for you, right? So let's look at this point right here. By the way, another typo. That point, the y coordinate's clearly 1. What happened here is I initially made one choice, and then I decided, let me avoid the fractions by changing some. I just forgot to change that, so that was an oops. So please make that correction. Y is 1 for this point. And let's think about how we can write that point down in spherical coordinates. So the first one is a freebie. The first one is to notice that this is in this plane there like that, where that theta is pi over 6. Oh, by the way, with the angles, always plus, any integer multiple of 2 pi. So you'll see plus 2 pi m, plus 2 pi n. That just means, of course, any angle, you can add 2 pi and it doesn't matter. Okay. So, theta is pi over 6, thus putting you in that plane. You can then think, okay, well then I need to know in that plane, what is this angle from the positive part of the z-axis, and you look at the numbers and realize that there's a little 45, 45, 90 triangle down there, thus making that phi pi over 4. Excuse me. And therefore, I can, subsequently I can look at this distance. Here we go. That distance, easily computed from the several right triangles, and it's 2 square root of 2. So that's one option. That's sort of the nicest option for how to describe that in spherical coordinates. But notice there are different. I didn't want to erase that. There are different ways that you can go on this. So here's an alternative. Also thinking about the point in this plane, where theta is pi over 6. Weird, this is going to seem, but notice that instead of doing that for the angle, I could instead think about rotating sort of backwards, right, in that plane. If I go all the way backwards by 3 pi over 4, so thus phi is negative 3 pi over 4. Notice that gets me going in exactly the right direction, or should I say exactly the wrong direction. And thus, I can get to that same point with rho equals negative 2 root 2. Right, so you're going to have this little bit of mental gymnastics about thinking about the angles, and if you go back, right? So it's like I say, it's a good exercise. Think it through. Try to draw a good picture. Really helps a lot, right? And think through, and I want to encourage you to do the remainders on your own, but think through that this works too, and so does that one. And like I say, it's a little bit of mental gymnastics. Okay. All right, this makes a pretty good stopping point. I'm going to show you a neat example, a neat application of this next time, and we'll go on to other things. Okay, see y'all later.